Hi guys, Audrey here. So today we're going to see an example of a differential equation. The last time we saw exponential growth. If you haven't watched that video yet, you definitely should. Today we're going to see how we can use differential equations word problems to model the situation in South Korea with COVID-19, which has been growing at a little bit of a different rate. Okay, so first let's read the problem. Let us assume that in South Korea, the rate of people infected by COVID-19 is growing logistically. Based on the given data, the number of people infected seems to be approaching a carrying capacity of 9,000. On January 24th, there were 2 known cases. On March 2nd, there were 4,812 people infected. We want to know how many people infected, and we want to know how many people would we expect to be infected on, well, here it says March 16th. Yeah, March 16th. Okay, so the first thing is, what is this carrying capacity? Well, to understand that, maybe we could talk about rabbits for a second. So let's say that I have a rabbit. That's not a rabbit. So, and then I have like a giant field of carrots. Okay, well, this rabbit right here can eat all the carrots he wants. He's going to be super healthy. He's going to be great. And then he's going to have babies. So maybe he's going to have, like, I don't know, like rabbits have lots of babies. Okay, but what that means is there are then more rabbits eating the carrots, right? So there will be less carrots for each rabbit. And then these rabbits have more babies, and they have lots more babies. Which means now there are even more rabbits, which means there will be less carrots for each of those rabbits. But the carrots aren't growing, only the rabbits are growing. So eventually what's going to happen is the environment is no longer going to be able to support those rabbits. And so instead, it will start having less babies, and the rabbit population will grow more slowly. In the beginning, it's growing really, really, really fast, but soon the environment's not going to be able to support it. There's some number of rabbits that it's not going to be able to go above because the environment will not support those rabbits. So this is the idea of carrying capacity. It's the maximum that can be sustained by a given environment. Okay, so now we understand what carrying capacity is. Let's understand what logistic growth is. In the last question with exponential growth, we were able to read our differential equation directly from the sentence. We're not going to be able to do that this time. So we're going to understand what logistic growth means. What does it mean that this thing is growing logistically? Well, let's start off the same way as before. We're going to define a new variable. N of t is equal to the number of people in South Korea infected at time t, which means that dn dt will be the rate of change of people infected. In other words, how fast the number of infected people is growing. Okay, so we want to define dn dt. And we're going to understand what logistic growth means when we do that. Well, first, it means that in the beginning, before we have like not enough carrots, for example, this is going to be growing at a rate proportional to the amount of rabbits that there are, or in this case, the amount of people that are infected. So here I'll have k times n. In other words, in the beginning, the growth rate is going to be exponential, the same as what we saw occurring in Italy. But, so what's happening in South Korea is they've made all of these like social distancing idea. They've been cutting off people from each other. So they've been stopping the virus from having like a place to go. In other words, they've been limiting the environment. They've been taking away the carrots from the rabbits. So in the beginning, it's growing exponentially. But what's going to happen is over time, that growth rate is going to get smaller, like this. So notice here that when n is really, really small, n over 9,000 is also really, really small. So what that means is the rate of change is really close to just being k in. That value there that we just added, this like 1 minus in over 9,000, is pretty much 1 when in is really, really small. However, as n gets closer and closer to 9,000, as we're cutting off the place for that virus to go, or if we're cutting off the amount of carrots that these rabbits have to eat, then slowly this value right here is going to 0. So that 1 minus n over 9,000 is approaching 0 as n approaches 9,000. So what that means is even though it starts growing exponentially, as n gets closer and closer to 9,000, that growth rate is going to be slowing down and getting slower and slower and closer to 0. Okay, so then the next question is, how do we solve this differential equation? The same as we've been solving other differential equations. So the first thing I'm going to do is I'm going to multiply both sides of this thing by 9,000. So that way I don't have that fraction over there. And what I will end up with is 9,000 dn dt is equal to k n times 9,000 minus n. Oops, minus n. Next, I will multiply the dt over and multiply those n's over to get 9,000 over n times 9,000 minus n dn is equal to k dt. So we've said in the past that typically we want to keep all of our constants over on the t side. Well, that 9,000 we're going to keep over on the inside for the time being because it actually is going to make this a little bit of a simpler problem in terms of the partial fractions that we're about to have to do. So now I'm going to take the integral of both sides. And over here, that's pretty straightforward. It becomes kt plus a constant. But over on this other side, let's call this star. How would I do this integral? And the answer is partial fractions. I have a polynomial over a polynomial. I've got a rational function here. I have 2 linear factors in the bottom. So we're just going to do a partial fractions decomposition. To get a over n plus b over 9,000 minus n, which gives us 9,000 is equal to a times 9,000 minus n plus b n. Now the zeros of my denominator there, we're going to let n equal to 9,000, which gives me that 9,000 is equal to 0 plus 9,000b, which gives me b equals to 1. And my other 0 here was n was equal to 0. And when we plug that in, we end up with 9,000 is equal to 9,000a, which gives me a is equal to 1. So the integral that we end up with here is the integral of 1 over n plus 1 over 9,000 minus n, which gives me natural log of n minus natural log of 9,000 minus n. Now that minus comes from the fact that the derivative of 9,000 minus n is -1. That derivative is just a constant, so we just have to multiply by 1 over that constant. This becomes minus ln of 9,000 minus n. All right, so let's go put that over here in our differential equation. Ln n minus ln of 9,000 minus n is equal to kt plus c. Okay, now we want to solve for n. So I'm going to do a little thing right now that might seem a little bit weird, but that's going to make this a little bit easier to solve for in the long run. I'm going to take both sides of this equation and I'm going to multiply it by -1, which gives me ln of 9,000 minus n minus ln n is equal to -kt, and we'll just call this C1. Okay, now remember our log rule. Ln of a minus ln b is equal to ln of a over b, giving us ln of 9,000 minus n over n is equal to negative kt plus a constant. We're going to put this e to the power of both sides. So we'll end up with 9,000 minus n over n is equal to e to the negative kt plus c1. Great. Okay, so now what's going to happen? Well, we're going to actually see why I multiplied by that negative. Multiplying by that negative resulted with me having 9,000 minus n on top instead of n on top. So I can use that denominator now to separate the numerator and end up with 9,000 over n minus 1 is equal to, at this point, that plus c1, I'm going to do with my little constant thing, and I'm going to bring it down to the front. I'm also going to remember what we did with the exponential problem. I'm going to think of this as either negative k to the power of t. And now it's pretty straightforward to solve for n. I get 9,000 over n is equal to c e to the negative k to the power of t plus 1, which means that n is equal to 9,000 over c e to the negative k to the power of t plus 1. So this right here is my equation representing the number of people infected. Now we need to solve for c and we need to solve for k. So we're going to use our two initial conditions to do that. Initial conditions. Well, if we were told that on January 24th, there were 2 known cases, and on March 2nd, there were 4,812 known cases. So January 4th then is going to be our day 0. So t equals 0, and there were 2 cases. And then when t, well, actually, on March 2nd, I believe we said, let's look again because I forgot already. On March 2nd, so on March 2nd, if January 24th is t equals 0, well, then there are 7 days left of January, plus the 29 days in February, plus the 2 days of March that we have here. So that's 7 plus 29 plus 2, which gives me 38. So I have t is equal to 38, n is equal to 4,812. Let's plug in our initial conditions. So we'll have 2 is equal to 9,000 over c e to the negative k to the power of t plus 1. The power of t in this case, that's 0. So all of that little thing right there becomes a 1. So then I have 2 times c plus 1 is equal to 9,000. So c plus 1 is equal to 4,500. So c is equal to 4,500 minus 1. That is not a 4,500. Added an extra 0. So c is equal to 4,490. Good. Perfect. Okay, so now we want to plug in what's happening over here with our t equals to 38. So we'll end up with 4,812 is equal to 9,000. Our c was 4,490. E to the negative k to the power of 38 plus 1. Oops. The power of 38 plus 1. So now we want to solve. Remember, we're not going to solve for k here. We're going to solve for e to the negative k. So e to the negative k then, we'll have 4,812 times 4,490 e to the negative k to the 38 plus 1 is equal to 9,000. So 4,490 is 9,000 over 4,812. Which gives me 4490 e to the negative k to the 38 is equal to 9,000 over 4,812 minus 1, which gives us 349 over 401. Which gives us 9 over 40. So the power of 38 is 349 over 401 times 1 over 4490. Now we're going to take this and put both sides to the power of 1 over 38 to give us that e to the negative k is equal to 349. This is having some issues today. 304. What's happening? 349 over 1,800,190 to the power of 1 over 38. So that's kind of a gross number. We're just going to stick it into our differential equation as is, not worry about the fact that we have a complex fraction here. So we end up with n of t is equal to 9,000 all over 4,490 times 349 over 1,800,490 to the t over 38 plus 1, and that right there is, this is the equation that represents the number of people infected at a given time. Now, we want to use this to figure out how many people we think would be infected on March 16th. That said, let's start by graphing this thing. So we saw that with the exponential growth, it started at a certain place and it just got bigger and bigger and bigger. With this logistic growth that we have just done, there's actually an inflection point that occurs. Now remember, an inflection point from Cal 1 is when it goes from concave up to concave down. In other words, concave happy to concave sad. But we're actually really happy that this happens because, so this is going to be my 9,000. Oops, I erased the whole thing. So this, my 9,000 is going to be sort of like a horizontal asymptote, or it is a horizontal asymptote rather. We started at 2, it grows exponentially, but then slowly as it gets closer and closer and closer to that 9,000, that carrying capacity, that growth slows down. So let's see if we can figure out what would happen on March 16th. So on March 16th, remember that we had 7 days left in January, plus the 29 from February, plus the 16 in March. That puts us at day 52. So n of 52, we just plug it into our equation. It's really gross. We definitely need a calculator to do this. So I'm just going to plug it in for you. And we get 8,676, which, if you check Wikipedia, is actually pretty close to what was actually happening on March 16th. Anyway, I hope this gives you an idea of a real-world application of differential equations. Bye, guys.